Hello everyone, thanks for watching this video. Today I am going to talk about our work GSN, which is an advanced generative steganography network that can generate realistic stego images without using cover images. We will introduce it from the following 4 aspects. First, we will introduce the differences between steganography and generative steganography, and the problems faced by existing generative steganography. Then, we focus on the GSN method we proposed and its experimental results. The upper framework is traditional steganography and the lower framework is generative steganography. Traditional steganography hides secret data through modifying cover image, while generative steganography does not need cover image. In generative steganography, the generator and the extractor are 2 independent neural networks. The generator directly generates a realistic stego image through secret data, and the extractor can extract secret data from the stego image. Compared with traditional steganography, the synthetic stego images have high visual quality and conform to the statistical characteristics of natural images, and generated stego images do not have image distortion owing to hidden secret data. Thus, the generated stego images have high anti-steganalysis ability and generative steganography has higher security. The existing generative steganography methods can be divided into 4 types. The first type can generate fingerprint or texture stego images. It has the advantage of relative high extraction accuracy, but the disadvantage is that the content of the generated image is unnatural and the hiding capacity is low. The second type needs to synthesize cover image through the network first, and then hides secret data into the cover image. Its advantage is high hiding capacity, but its disadvantage is easy to be detected by Steganalyzer. The third type is generating stego images through invertible networks, with advantages of high hiding capacity and invertible process, and disadvantage of poor robustness. The fourth type is to map the label Y and the latent variable Z into the generator of GANs to synthesize the stego image. The generated image is natural and realistic, but the hiding capacity is low. We list the shortcomings of the existing generative steganography methods and the improvements of our work. We are the first to save stego images after quantization, which is useful in reality. The size of the synthesized image in our work is not limited, even up to 1024 x 1024, which mainly depends on the display memory capacity. When synthesizing large images, the payload can still reach more than 1 bpp, and the image quality will not decrease with the increase of image size. The hiding capacity, extraction accuracy and visual quality of this scheme are significantly improved. The hiding capacity can reach tens of thousands of bits, and the extraction accuracy is about 97%. However, there are 2 unresolved points. One is that the key is not used between the sender and the receiver, and the security cannot be guaranteed. The other is that the generated stego images have poor robustness and cannot be compressed by JPEG. The proposed GSN contains 4 subnetworks: a generator G, a discriminator D, a Steganalyzer S and an extractor E. Discriminator D and Steganalyzer S are used as 2 discriminators in GANs, which can ensure the visual quality and reduce the difference between generated cover, stego images, respectively. The inputs of GSN include a latent vector, a noise matrix or a 3-dimensional matrix of secret data. The generator can produce a cover image when latent vector and a noise matrix are input. Also, A stego image can be generated when inputs are latent vector and secret data. Then, real image and the generated stego image are sent to the discriminator to decide whether they are real or fake. Meanwhile, the generated cover, stego images are fed into the Steganalyzer for differentiation. The generated stego images are input to the extractor E to get predicted secret data. We can see the structure of generator G, which contains several general blocks and a newly designed secret block. The function of the secret block lies on two aspects. 1. It enables the generator to synthesize cover or stego images when noise or secret data is input. 2. It removes the defects on image contents and improves the quality of stego images. We can input noise or secret data into the secret block, and then noise or secret data is added to feature mapped pixel by pixel to generate a cover or stego image. Low-pass filter is used to filter image flaw in secret block, which can improve the image quality in visual. The overall optimization objective consists of three small optimization objectives, that is, adversarial loss between G and D, adversarial loss between G and S, and the mutual information between secret data and stego image. In adversarial loss between G and S, Steganalyzer S hopes to output the correct predictions with binary cross-entropy loss, while G wants classification rate of S close to 50% for both cover and stego images. Both G and S aim to minimize these two losses. In order to achieve secret data could influence the image content, and it can be recovered exactly from stego image. The mutual information between secret data and stego image is expected to be maximized. We use a variation lower bound to approximate the mutual information between secret data and stego image. Only when the extracted secret data is equal to the input binary secret data, the maximum value of variation lower bound is reached, and thus mutual information is maximized. The loss function of each subnetwork is composed of the above optimization objectives. The loss function of the generator is composed of the adversarial loss for G between G and D, the adversarial loss for G between G and S, and a regularization item, which is for stable training. Discriminator's loss is added by the adversarial loss for D between G and D and a regularization item. Steganalyzer's loss is the binary cross-entropy loss. The loss of extracting hidden secret is computed by the binary cross-entropy loss. Here, we add random noise to generated stego images for improving the robustness, and it can effectively improve the accuracy of data extraction after image quantization. Both G and E are optimized to minimize this loss. To effectively train our GSN, subnetworks G, D, S and E are optimized sequentially as illustrated in Algorithm 1. G and E are optimized simultaneously to improve the secret extraction accuracy, where a hierarchical gradient decay skill is applied to improve the resistance against steganalysis methods. We propose the hierarchical gradient decay skill to reduce the differences between generated cover and stego images. It works because the HGD skill force G to hide secret data in high-frequency image details. Steganalysis tools often use the differences of cover, stego images for classification. Once their differences are minor and untraceable enough, steganalysis algorithms are hard to detect the stego images. We find that the proposed secret block is responsible for generating image details while the earlier layers tend to generate low-frequency signals, like shapes and colors of images. thus reducing the earlier layer's gradients of secret extraction loss forces to hide the secrets in high-frequency image details. Next, I will show some experimental results. Secret data's extraction accuracy decreases gradually as the payload increases. When the payload is 1 bpp, the extraction accuracy values are over 97% for both datasets. Besides, our scheme achieves excellent undetectability regardless of payloads, where the pay values are close to optimal 0.5. There are 128 times 128 stego images of faces with various payloads. Stego images of top row are with the payload of 1 bit per pixel, and stego images of the bottom row are with the payload of 8 bits per pixel. There are 256 times 256 stego images of bedrooms with various payloads. Images from the leftmost are with the payload of 1 bpp, and images from the rightmost column are with the payload of 8 bpp. They are ROC curves of different steganalysis algorithms. For steganography, the optimal ROC curve is the counter-diagonal, and the optimal AUC value is 0.5. As we can see, our ROC curves and AUC values are close to the ideal results, which indicates our proposed GSN is very safe. Our stego images are generated with two inputs, latent vector Z and secret data D. We generate two stego images with different D but the same Z, using a well-trained GSN model. We can see, when D is varied, these two stego images only differ in image details, such as texture and edges. By modifying the input latent vector Z, the appearances of stego images are changed drastically. We compare our work with two types of steganographic methods. One is traditional steganography schemes based on deep learning, which need cover images for data embedding. Another one is generative steganography, GS. Works that can generate stego images without cover media, including tailored GS and DL-based GS methods. Most DL-based TS methods have poor steganographic security, while our proposed GSN achieves better security performance with higher pay values. Compared to tailored GS schemes, our GSN can generate realistic natural images with a much higher payload. In DL-based GS schemes, our GSN outperforms the other works overall. The payload is more than 11 times higher than that of theirs. Meanwhile, better ACC and pay values are obtained. What's more, our work can generate stego images of higher quality. This slide gives a visual comparison among different GS methods. We can see our stego images are more natural with a lower Ni-K score and a higher payload. That's all about this report. Thank you.